Section 5.5, Double Angle Identities. These are our double angle identities for cosine, sine, and tangent. They are derived in the first part of Section 5.5. Let's take a look at an example. I'm given cosine theta equals 3/5, and sine theta is less than 0. They want me to find sine 2 theta, cosine 2 theta, and tangent 2 theta. Let's begin by finding out where we're located in our quadrants. I have a cosine theta which is a positive 3/5, and I have a sine theta that is less than 0. That tells me I need to be in either quadrant 1 or quadrant 4 for cosine theta to be positive. But since sine is negative, that tells me I'm in quadrant 4. I need to find the sine of theta first. To do that, I'm going to use sine squared theta plus cosine squared theta equals 1, our Pythagorean identity. I can find that because I already know the cosine of theta, and I can just substitute in. Here I have sine squared theta plus, and when I square 3/5, I get 9/25 equals 1. Sine squared theta, and when I subtract 9/5, 1 minus 9/5 gives me 25/25 minus 9/5, which is 16/25. Then I take the square root of both sides. I get sine theta equals plus or minus. When I take the square root of this, I get 4/5. But I know that I'm in quadrant 4. In other words, sine theta has to be less than 0, and cosine is positive. So it tells me that sine theta is a negative 4/5. Now, I can use one of my identities from my double angle identities to find the sine of 2a. And I can use this one because I know the sine of a and the cosine of a now. So I have that placed here. All I have to do is substitute in, bring down sine 2a equals 2. Sine a I just found to be a negative 4/5. And cosine a was given to be 3/5. And when I simplify, I'm going to get sine 2a equal to negative 4 times 3 is a negative 12 times 2 is a negative 24 over 25. Now what I want to do is find cosine 2 theta, and I have the identity down, one of the forms, to be cosine 2a equals cosine squared a minus sine squared a. From the previous slide, I know that cosine theta is 3/5, and I know that sine theta is a negative 4/5. So all I have to do is substitute in for cosine, 3/5 squared minus sine, which is a negative 4/5 squared. Take the square of both. That's going to give me 9/25 minus 16/25. And cosine 2a is equal to 9 minus 16, which is going to give me a negative 7/25. In the last part of that first example, they want me to find the tangent of 2 theta. To do that, I need to find tan first, and I know from one of my previous identities that I know tangent theta is equal to sine theta over cosine theta. And I just substitute my known values from the previous slides, negative 4/5 over 3/5. And when I invert and multiply, I'm going to get tangent theta to equal a negative 4/3. Now I can substitute those values into my double angle identity for tangent. That gives me the tangent of 2a equals, or theta, 2 tan a, which is 2 times a negative 4/3 over 1 minus a negative 4/3 squared. Simplifying, I get a negative 8/3 over 1 minus 16/9. I simplify again, negative 8/3 over 1 minus 16/9. That gives me 9/9 on the bottom, which is going to give me a negative 7/9. And when I invert and multiply, that's going to give me a positive 24 over 7 for the tangent of 2a. Let's continue with our next example. I want to use identities to find values of sine and cosine functions for each angle measure. Here I want to find theta, and I'm given cosine 2 theta equals 2/5, and theta terminates in quadrant 1, so I know my values will be positive. I want to find cosine and sine theta. We can find sine theta by using this identity, because I'm given cosine 2 theta, and this is the double angle identity for cosine, but I can come out with just sine if I can simplify. So I'm going to use cosine 2 theta equals 1 minus 2 sine squared theta, and then substitute my known value. Here cosine 2 theta is 2/5. I just substitute in. That's 2/5 equals 1 minus 2 sine squared theta. Let's subtract 1 on both sides. When I do, that's going to give me 2/5 minus 1, or 5/5, which is a negative 3/5 equals a negative 2 sine squared theta. I can divide by a negative 2. That's going to give me a positive 3/10 equals sine squared theta. Take the square root of both sides. I get sine theta equals plus or minus the square root of 3/10. When I rationalize, that's going to give me plus or minus the square root of 30/10. But since I'm in quadrant 1, I know that sine theta is positive. Therefore, this is a positive square root of 30/10. Now I need to find cosine theta. I can either use this identity or this identity, because I can generate cosine theta. If I use this identity, I just found sine, but if I mess up finding sine, then I will mess up this answer. Therefore, I'm going to use this solution. But if I did find sine correctly, both solutions will give me the same value. So let's use the bottom one. Cosine 2a equals 2 cosine a, or theta, minus 1. Substitute. I know cosine 2 theta is 2/5 equals 2 cosine squared a minus 1. Add 1 to both sides. 2/5 plus 1, or 2/5 plus 5/5 is 7/5 equals 2 cosine a, or theta, squared. Divide by 2, that gives me 7/10 equals cosine squared theta. Take the square root of both sides. I get cosine theta equals plus or minus the square root of 7/10. And when I rationalize, I'm going to get plus or minus the square root of 70/10. But I know that theta terminates in quadrant 1, therefore cosine is positive. Therefore, cosine theta equals the square root of 70/10, and that would be positive. On the next example, they want me to use identities to find the values of sine and cosine functions for each angle measure. They want me to find the sine of 2 theta and the cosine of 2 theta. Given the sine theta is 3/5 and cosine theta is less than 0. When cosine is less than 0, that means it is in quadrant 2 or 3. Sine is positive in quadrant 2 and 1. Therefore, these must fall in quadrant 2. I can find cosine 2a quickly, or cosine 2 theta quickly, by using the double angle identity, because I'm already given the sine of a. So I can use the double angle identity of cosine 2a, or 2 theta, equals 1 minus 2 sine squared theta. Then substitute my known values. Cosine 2 theta equals 1 minus 2, and sine is 3/5. But when I square it, that's going to give me 9/25. And when I simplify, cosine 2 theta is equal to 1 minus 18/25. Therefore, cosine 2 theta is equal to 25 over 25 minus 18 over 25 is going to give me 7/25. Now, I need to find the sine 2a. I need to use this double angle identity. To do that, I have the value of sine. I need to first determine the value of cosine. I can do that by using our Pythagorean identity. Therefore, when I substitute in, I can have sine squared theta plus cosine squared theta equals 1. I know sine squared theta is 9/25 plus cosine squared theta equals 1. Subtract 9 squared theta from both sides. I get cosine squared theta equals 1 minus 9/25, and that gives me 25 over 25 minus 9/25, which is going to give me 16/25. Therefore, I know that cosine theta, when I take the square root of both sides, is going to be plus or minus 4/5. But I am in quadrant 2, and I know cosine is negative, therefore I'm going to use a negative 4/5. Now, I can use my double angle identity, sine 2a, or 2 theta, equals 2 sine theta, cosine theta. And then I just substitute in sine 2 theta equals 2 times, I know sine to be 3/5, and cosine I just determined to be a negative 4/5. And sine 2 theta is equal to 3 times a negative 4 is a negative 12. A negative 12 times 2 is going to give me a negative 24 over 25. On this example, they want me to use an identity to write each expression as a single trig function value or as a single number. I'm given cosine squared 7x minus sine squared 7x. If I take a look at my double angle identities, it's very close to that identity. So I could write below it cosine 2a equals cosine squared a minus sine squared a. And what value represents a in my given information? A is equal to 7x. So if I substitute that in, a is equal to 7x. Therefore, cosine 2 times a, and I know a to be 7x, is equal to cosine squared 7x minus sine squared 7x. Then I can solve my problem by just multiplying. This simplifies to cosine 14x. And now that's written as a single trig function. On this problem, I'm given the same example. I want to use an identity to write each expression as a single trig function value or as a single number. I'm given sine of 15 equals cosine 15. That's very, very close to this identity, except there's not a 2 in front of it. Well, what if I solved this for just sine A cosine A? So if I solved this for sine A cosine A, I would just divide by 2. Therefore, I would have 1/2 sine 2A equals sine A cosine A. And in my problem, A is represented by 15. Therefore, I could substitute that value into 1/2 sine 2A. 1/2 sine 2 times I know my value for A is 15. That gives me 1/2 sine of 30 degrees. And from our unit circle, I know sine of 30 is 1/2. So I have 1/2 times 1/2. Therefore, my solution is 1/4.